see if this is working. Very good. So, I'm Reid Sanders. I'm a machine learning consultant, and I'm going to discuss deep Q learning. In general, deep Q learning is a type of reinforcement learning, which we'll also cover, but we'll focus on deep Q learning. First, let's talk about what we're trying to accomplish. We're going to review reinforcement learning. We're going to discuss Q learning. And then we're going to discuss the advancement of Q learning, or the extension, deep Q learning. We're going to play some games. And we're going to talk about some of the future of the field, some improvements that you can do. And at the end, we're going to show you how you can do it yourself, because the big advancement in machine learning nowadays is that there are great models, there's great data sets, and the hardware has gotten to the point where an individual can experiment with deep learning or machine learning in general without much difficulty. So here's an example of a couple of problems, just to whet your appetite. On the left, for the robotics people, I hope that your robots look a little bit better than that, but this is an 18-dimensional model with continuous control that is learned completely model-free. So it has no knowledge. All it's doing is getting punished when it falls. So it learns to stay up. And on the right, we may not have a video after all. Yeah, I will show the videos at the end, I guess, so as not to risk getting off topic. This is a game, Atari game, people might remember it, and one of the biggest advancements in recent years is DeepMind's publishing of human-level control in Atari games. They basically figured out a method to make a deep Q learner that did not diverge, which is something we'll discuss later, and could solve many different Atari games with the same model. This is different than a game AI where you have a human going in and telling it what to do, or even a deep reinforcement model, a deep learning model such as you might have previously, where you have a game that you have to hand tune the features and exactly what's important about the game. Like with Breakout, you would consider that the ball is the important thing that has to track. So as a hand-tuned feature set, you would have to tell it where the ball is. In this model, it's just getting the raw pixel input and the raw score. And that's all it needed to learn a number of different Atari games. We'll discuss that more later. So first of all, we're going to have to go back. So apparently my conversion from LibreOffice did not work quite as well as I'd hoped. However, what is a machine learning basics? You have inputs, which is just the data about the system. You have outputs, which is the correct answers. You have your learning algorithm, which you can think of as your brain. And you have your objective function, which measures whether you're getting your answers correct, like whether your brain is estimating the world correctly or not. And then the optimizer, which changes your learning algorithm based on how far off and in which direction you are from the real world. So in reinforcement learning, we can replace these with a state instead of data, because this is what you observe about the world. You take actions, and these then receive a reward or not, and then your optimizer has to try to change your learning algorithm in order to maximize your cumulative future reward. In a supervised learning system, you have a labeled data set, which means that when you put in your inputs, you have the correct outputs, the things you want to see. If you have a bunch of cat photos and you're trying to tag cats, then you have the cats outlined by a human. This is the correct answer, and that you want your data set, your learning algorithm to learn. This is a lot easier, and is in fact something you can do with no difficulty right now. If you go down and download, say, AlexNet or ImageNet, you can run on your computer something that will detect a wide variety of categories, such as cats. However, if we want to be more like the real world, we're not going to have the correct answers, necessarily. When a baby learns how to recognize a cat, yeah, it'll have a couple of times the parents will say that's a cat. But mostly, it has to learn by being rewarded when it learns that if it rubs the belly, it gets clawed, or rewarded with a negative reward, and rewarded with a positive one when it recognizes that that's not a cat and doesn't walk into the street, for instance. So the difficulties here is the reward is delayed, oftentimes. In the game of Breakout, you get the reward when you hit the blocks, because that increases your score. But the reason that the ball hit the blocks is because 10 frames ago, you moved your paddle to the left so that it bounced off it. This is not immediate returns, so it might think that, oh, the jiggling over in the corner that I was doing is what caused me to get the reward when the ball hit the blocks, even though that's not true. And the rewards are not immediate, are not just not immediate, but they're sparse. They can be very sparse if you have a large state space. This is problematic when you consider planning for the future, and it's problematic just because learning algorithms typically require a lot of information. So if you want to learn something well, it needs way more training data than a human would, on the order of millions, billions of examples. So there's also the, as I mentioned, the credit assignment problem, wherein if it does one action over here, and then it receives an award, which is because of something else that happened a long time ago, then it will start assigning that credit, or rather it will have to decide which to assign credit to. There's also an issue that in the real world, you don't have nice discrete systems. And here, for most of the games we'll be looking at, it is a fairly limited world. But that's because the real world has a lot of degrees of freedom, a very large both action space, things that you can do, and state space, things that you can observe about the world. There's a lot of information. So we're going to be limiting our view typically to a small limited game, because that's what our systems can handle at this point. However, it's worth pointing out that in the last couple of years, the advancements in this, taking from toy models into something much closer to the real world, those advancements have been very impressive, and it is really a very fast-moving field with some extremely exciting developments. So, some basic approaches. As I discussed before, there's the policy iteration / gradient. This means you have a policy, which is a plan about how to take actions, and you change your policy based on the information you receive. So you try something, you get a reward or not, and you change a little bit. The gradient approach has the advantage that you know which direction to change towards. This is also, if you're doing a gradient descent, which is a very common optimization technique, that's an example of this. So most of these will fall under so-called temporal difference, which is basically you look at the difference between what you expected before you took the action and the difference after you took the action. So you look at your predictions and you get a little bit more information, and you recheck your predictions and change your old algorithm such that your old prediction matches what you know you now should have predicted. This makes sense. It's how we think. If we think, well, if we're in a chess game, we think, should I play move A or move B? When we play move B and lose horribly, we're like, maybe I should have played move A. Why did I decide to play move B again? And you change your mind. There's also a stochastic methods, which we don't assume anything about the world. We don't assume that it's differentiable. We don't assume that we know anything about it. It's just a black box. And these can be quite effective, but they also have some fundamental limitations, and they lose out on a lot of the power that, for instance, the differentiable approaches like gradient descent give us, that have had a great deal of success with unsupervised learning. So we're going to discuss the basic model that most of these work in is a Markov decision process. And all this really means is that you have, we have some rules about how the world works that helps simplify things and helps us compare models equally. So you have an agent which interacts with the environment. The environment provides states when the agent observes it. And the agent can take actions in the environment which then provide rewards. Remember that what we want is to maximize the future rewards. Now we have a policy, which is basically just our plan. How do we decide which action to take given the state? Now we have a couple of other things we have to consider. In general, a bird in the hand is worth 2 in the bush, or a bird right now is worth 1.2 birds 2 steps in the future. So this is the discount, which means that we appreciate rewards we get now more than rewards in the future. And then there's the learning rate, which is something that we simply have to consider. How fast do we want to change our algorithm? If we change it too fast, then it can tend to get stuck in local optima or just jitter around the place and never converge. Now, there's something called a Markov assumption, which is basically that history doesn't matter. The expected reward should only depend upon the current state and the action we choose to make. Now, this is obviously not true in many cases, but it makes it a lot easier. And in fact, you can include the important part of history in the state if necessary. So here's an example of a Q-learning, the simple Q-learning algorithm. All Q-learning is doing is looking at the current state. It chooses some action based upon its policy, which is then based upon your Q table in this example, and based upon some exploration strategy, which we'll discuss later. And then you take that action A that you chose, you'll observe some reward, and you'll observe the new state, and then you'll update your Q, which is your predicted reward, towards what you have now observed to be the correct answer, which is the current reward plus the max of all possible actions, the max Q of all possible actions from that next state. So you're in state A, you look around, you choose the max action, for instance. This is called the greedy exploration. You choose the max action, you step, you're in a new state, you look around at the possible actions, and you say, what's the maximum I predict, maximum Q value that I predict for all these actions? Basically, you run your policy again, and you say, okay, this one's my maximum, I got this reward, I add it to this, and that's what I should have predicted back there. That's what I should have predicted in the past. And then you update your Q such that that prediction was closer to what it should have been. So consider this example. This is a room diagram. Your goal is to get outside. You start in room 2. What do you want to do? Okay, first of all, here's our state action reward diagram. They simply have connections. We have a reward of 0 for everything that doesn't involve going outside, and if we transition to the outside, then we reach our goal state and get a reward of 100. So we start in 2, we know nothing about the world. All we know is that we can go to state 3, and that's it. So we check our Qs. Our Q value for state 3 is 0. Okay, it's the only state possible. It's the only action possible. We take our action and we look around again. Now we have 3 possibilities. We can go to 2, 1, or 4. All of these are 0. So let's just pick one randomly and choose 1. We go to 1. Now, we haven't updated our Q at all because we've received no reward and our Q is 0, so there's no update to do. We look around, we can go to 5, or we can go to 3. Look at our diagram. We're in 1. There's a reward of 100 to go to 5, and a reward of 0 to go to 3. So we go to 5. Then we receive a reward of 100. That's good. Congratulations, go us. I'm sorry. After we go to 5, we receive a reward of 100, and we update our Qs to say that when we transition from 1 to 5, we get a reward of 100. Now, we start again. We start in 2, we go to 3, we look at 4 and 3, let's say we go to 1 again. We look at 1 and 4, let's say we go to 1 again. Now, 1 on our diagram will have a Q value of something like 75 if we have a gamma of, based on our discount rate, right? It's not as valuable as the outside, but we know that it will lead to the outside soon. So we update 3, the action 3-1, based on the reward that we're expecting in the future from our previous experience. And so then 3 gets us another value, which is a little bit less than 1 in our Q table. And we can do this until we fill out the entire table. And then this is guaranteed to converge. Guaranteed to converge to the optimal solution. And it makes sense. This is pretty much a brute force approach in many ways. It's a little bit more efficient than that because we can, by backpropagating the information, we don't have to try every possible state. But we know this will converge. But it only works on relatively small problems. If we try to make a Q table, which is a brute force listing of all possible states and actions, and the rewards we expect from them, for a lot of problems, that just won't work. So, what's something that we can, something else to consider is that this is off policy, which means that it doesn't consider exploration cost. As in, if you have a cliff and your algorithm has a exploration policy that involves occasionally randomly taking random actions, then you might go jump off that cliff, and that's not good. So, when we make our exploration strategy, this thing we didn't discuss earlier, one of the difficulties of reinforcement learning is the exploration versus exploitation paradox, wherein if we explore, then we might be missing out upon taking advantage of the actions that we already know are good. The classic example of this is the multi-armed bandit, which is a term for slot machines in this case, or a bank of slot machines. And if you have a bank of slot machines with different probabilities of paying out, and you want to try a few of them to see which ones are more likely to pay out better, but at some point you need to decide, okay, I'm going to stick with this slot machine because it obviously pays out way more than the rest. This is assuming there's actually a difference. But now, in this problem, one way to do this is the epsilon greedy strategy, which is where we start with a random chance of exploring, epsilon, And this just means that each step will say there's some probability that we'll either take the maximum predicted Q value or we'll just do something random. And one way to do that, you can start with a high epsilon and then decay it as time goes on as you've understood the environment better, basically. So consider the real world that we were discussing earlier. If the search space is too large, then the Q-table approach isn't going to work. The Q-table approach has a nice thing about being optimal, but you can grow exponentially when the search space grows. So, what is deep Q learning? All it's doing is replacing the Q-table with a deep network to function approximate Q. So, Q, which is for SA, which is all the state and the action, it will predict your future reward, your cumulative future reward, is then going to be estimated by your network instead of drawn out of your table. This is pretty simple, but there's some difficulties. There's a classic case of TD gammon, which is back in '92, someone took the time difference and took a, I think, 50-layer multi-layer perceptron, and basically did this with a little bit of an older algorithm, and beat gammon. Gammon is, by beat I mean they perform superhumanly. All right, I will try to talk a little bit louder. Does this work? All right. How about now? All right. So it beat gammon, which means it performed superhumanly. It discovered, or backgammon. It discovered strategies which humans had never considered. One advantage of this approach is not only do you not have to have a human telling things what to do, but if it's figured out how to play with no human input, it doesn't have human biases. So when it learned how to play backgammon, it learned things that humans never thought of, or that they had discounted and just stayed in the rut of regular human play. And now the same thing is happening for many other games. For instance, you've heard of AlphaGo. That's an extension of this approach. You can learn things by having a computer with a novel approach. So, some basics of EQ learning, how you can improve it beyond just replacing your Q with, beyond just replacing your Q with a network, you can improve it in some ways. One of the most important methods is the experience replay. So if you start with, if you just train on each subsequent step, that has some problems because it can get into local optima, and it can drive, if you have some sort of a subset of the game that you're playing at that point, then it can drive you into optimizing for that too hard. So what you do is you store your experiences. All you have to do, you just have to store your state, the action, the reward, and the subsequent state. And this is your experience replay, and then you can take mini batches or just batches from this, train on those random batches, which, as you might know from regular machine learning, it's always a good idea to train on random batches from your data rather than just select one part of it. The exploration strategy that I discussed, there's some other methods like clipping the error and the rewards to prevent it from oscillating too strongly when it hits these really sparse rewards. Target networks, things that are beyond the scope of this. why this is zoomed in randomly. Okay, so this is our basic Q-learning loop. If we look at, here's our exploration strategy. If it's less than epsilon, then we take the maximum, or we take a random action. Otherwise, we use the prediction based on our Q. So if we either take a random action or the predicted maximum action. And if we take and this is our model code, which is just an example in Keras, which is a machine learning library with a very high-level abstract library, which makes it quite easy to build models. And this is really all the code you need to define your model. There's some other code to define how it actually interacts with your system, but it's pretty simple. You can look here, it's a sequential model. You have some convolutional layers to take the pixel inputs and take them down to something that your model can digest. And you have a few fully connected layers. And you can set your activations, and you can set your optimization, which is something we discussed earlier. There's several optimization algorithms, such as RMS prop or stochastic gradient descent, and you can set those. This is how far deep learning libraries have come. You can just write this, and it'll figure out the hard parts for you. You don't have to manually calculate your gradient or anything. So, this is playing catch. It's a very simple game. All it's doing is a block falls and it tries to catch it. It gets a reward if it catches it, and if it doesn't get a reward, or it gets a negative reward if it fails. We're going to discuss training a little bit, because we're going to show you how to do this later. And one of the most important parts of training the model is being able to figure out whether it's working and what hyperparameters to choose, stuff like that. So, in this, we have a couple of examples. On the top, we have a large network, a large deep network, and on the bottom, we have a single layer network. As you can see, it's not really very different. So for a game of catch, we have enough parameters to model it pretty easily. In fact, let's try cutting down the neurons even further. Instead of having 150 neurons, let's try 2. This is a 2x3 deep network. As you can see, this is the win percentage. So it's not doing too great. At 6x1, okay, it's a little bit better. Let's try with just 2 layers, but over 4,000 epochs. This is 4 times as much as last time. So we'll see whether with only 2 neurons, whether we can fit this game. So, as you can see, it reaches about 70%. It reaches about 70%. All right. It reaches about 70% win rate with just 2 neurons. This means that this is a very simple game, but if we train it long enough, then we can reach a pretty good accuracy. So what about a little bit more complicated game? This is Snake, as you might recognize. With Snake, we can also reach very high win rate. However, it takes a much larger model. This is 256 by 2 hidden layers, which means that we have 256 neurons in 2 different layers. And this is 1,500 epochs. Now, one of the important things about this is the experience replay. If we have unlimited memory, that means we store all the different actions in our memory. this works pretty well. However, if we set our memory to only 1,000, which you wouldn't think would make that much of a difference, but it does. Here we have it with 2,000 epochs, and it doesn't even reach, it only reaches about 60% win rate. So let's try this again with a couple of different hyperparameters. This is, once again, with 1,000 memory, which it means it stores the last 1,000 actions, action state, reward, view state, tuples, and with a 150 by 1. So as we can see, in the game of Snake, which is a much more complicated game than Catch, having a larger network makes a much bigger difference than it did with just playing the game Catch. Catch managed to get away with 2 neurons. This takes 256 by 2. Now, we could perhaps run it for more epochs, but it also takes a lot longer to train. What if we set our memory to only 100? Well, that's pretty bad. That's really bad, actually. So we can't really get away with just setting it to 100. One of the advantages of, you can look at the link there, that has a great blog post about using Neon, which is another, similar to Keras, it's a deep learning library. You can actually take your rewards, your expected rewards, at each state, and back propagate it to show what the network is looking at in the convolutional layers, what is being activated in the convolutional layers to make it predict that. So we look at, this is the game screen, and this is the activation. I don't know if you guys can see this, but for instance right here, that's the ball. So as the ball is coming, it's predicting what the ball is going to do, and it's focusing on the ball. It's recognized, in other words, that the important part of the game is what is the ball doing. So this is a nice way of visualizing what exactly is going on with your network. And you can actually learn a surprising amount by playing out the actual activations of the network. You might remember Google's Deep Dream does this with picture categorizers, and they can increase the activation of one of the categories and make it and show you the hallucinations as it looks for dogs and everything, for instance. Basically, what patterns is the network actually being activated on in the vision? So there's another nice advancement, the OpenAI Gym. Now, OpenAI is a initiative by a number of very well-regarded machine learning researchers. It's funded by members of the PayPal mafia, like Elon Musk and Peter Thiel, to the tune of $1 billion, and with the goal of keeping AI open. This is important because as keeping AI, which is what this is heading towards, which is what the goal for a lot of researchers with deep reinforcement learning, or reinforcement learning in general, is to reach good AI. And currently the tools available to do that are more open and available than at any other time in the past. However, there is some reason to believe that that might change in the future. You can look at, for instance, this DeepQ network model that DeepMind made has been patented by Google. So there's some reasons to worry about the future in terms of how open and available this will be. There's also considerations about hardware. For instance, Google just announced that for the past year they've been running all of these, a lot of their stuff on custom chips, custom ASICs, which is not something that a small company, and certainly not an individual, can get. So there's some reason to be, if you're interested in doing this yourself, or in simply having it be open and available for individuals, then this is a useful endeavor by a lot of very important people in the community.
to keep that open and available. And one of the first things that they've done is release OpenAI Gym, which basically takes a set of environments and standardizes the environments so that you can compare different algorithms. So you can look and see, you can compare whether when they're playing Breakout, is this algorithm actually better than this one? And you have reproduction notes and review. So if people can review other people's results and actually reproduce them, and then post a review, that makes it much more likely that no one's making a mistake and all the information about these algorithms is actually accurate. Something that I'm sure the scientists here have seen problems in academia where no one really wants to reproduce papers, they want to make their own new ones. There's also another example, a black box challenge, which is currently running, which is basically a black box game. You don't know what's going on, all you know is you have some actions, you can take them or not, and you get some reward. And the advantage of this is, even with these models which are supposed to be so-called model-free, as in they don't necessarily make any assumptions about the environment, and they're supposed to be generally applicable. In practice, that's a bit more difficult, and the researcher will typically take a model and think about it some themselves. They'll think about the game, think about how they might play it, think about the important things for the model to do, whether time is important, should I include a lot of memory or not, should I, is this going to do something that needs a deep model, or can I get by with a shallow one? These things are stuff that someone will have to consider when they're actually making a model to match a game, which maybe we shouldn't, because if we want to make a general system that can solve any game or any problem, then if we do too much thinking about it ourselves, then we're going to basically overfit the model. Here's some examples from the AI Gym. You can emulate various Turing machine functions, like copying from the tape and stuff. Go, which is another important recent advancement, AlphaGo, you've probably heard of, which is taking something of an extension of this effort to the game of Go, which has been considered to be one of the most difficult board games for a computer. And of course, continuous control, which I'm sure the roboticists are very interested in, where if you have, for instance, the cart pull problem, trying to balance something, or more Atari games, which we'll look at some videos in a second, hopefully. So some of the possible advancements, or things which if you're interested in, you can look up. Things that are making the field better, in other words. Double Q learning. Double Q learning basically tries to fix the problem that Q learning has, where it's typically too optimistic. Because it's looking at the maximum Q value, it tends to expect more rewards than it should. This isn't necessarily a bad thing, because, for instance, optimism can be a good exploration strategy, but and there's an interesting paper about double Q learning, which tries it on basically has two different Q networks, which cross-train each other on different experience replays. And this keeps them from being too optimistic, and has gotten some good results on Atari games. Trust policy region optimization. This is something I found on AI Gym. There's this one algorithm that had been doing quite well on a lot of the games. Basically, this works on the assumption that your model has a certain region that you trust it to behave well in, and then it can change that region based on returns from the environment. So if it tries this and it works, then it can say, okay, I guess I can trust myself to work well in that environment, in that region of space. a little bit better, and so it expands its trust region. And then actor critic for continuous action. The stuff we're working on here is generally discrete, which means it has a lot of advantages, but the real world is more continuous. And so this basically has instead of just like manually slicing up the continuous into a discrete regimes, this has a critic which looks at it and does the same thing for you. Here's an example of how to run your own. Now, you can look at the slides later, so we aren't going to go through this in detail, but even if you don't have a good computer, you can run it on Amazon's EC2, for instance, or you can run it on Femora, which has a free trial for GPU machine learning. And there's a variety of other providers which can train your models in the cloud. And of course, if you have a good GPU, then you can train it on your computer. It's actually quite simple to get into at this point. You can just download something from GitHub and follow a few simple install instructions and be running within an hour to day, depending on the technical difficulties. Some more resources which you might want to look at. And I'm going to try to play you some Atari videos. As you can see, it's pretty good. It's important to remember that this is trained versus itself. There's no human input. It doesn't watch a human play. It is trained without knowing anything except for the pixels on the screen and the score, and possible actions. There's about 5 projects that I know of reproducing this, which goes to show exactly how important this was in the minds of the community. It solved one of the bigger problems of one of the reasons why this is so important is it solved one of the bigger problems that had been around for 20 years. Since TD Gammon, people have tried to apply basically deep Q learning to other games and have found serious problems. Mainly that the models tend to diverge. This is for a variety of reasons. Part of it's just when you take a nonlinear function approximator in this regime, you don't have any convergence guarantees. And the main thing is they discovered that yes, you can make it converge with current techniques. And so for the past 20 years, we've been typically using linear approximators because they converge better. But the power of a neural network, a nonlinear function approximators in general, can be applied to reinforcement learning, and that's basically what the DeepMind paper showed. And now it's being applied to a lot of things, as I discussed previously. So, I'm sure I've got something, but any questions? No proofs there, unfortunately. Yeah, we know that Q learning, for instance, converges, but deep Q learning, You can make some assumptions about it depending on the system, but it tends to be a much more restricted system than you want to actually make a proof about it. Most of the time, advancements on the edges of machine learning, or specifically deep learning, tend to be of the not so much of the mathematical proof side, unfortunately. They tend to be, well, maybe not unfortunately, they tend to be experimental. We look at this and say, this works pretty well, and then trying to figure out why exactly. Although there is advancements, there certainly is a place for looking at it mathematically and trying to prove things about restricted systems, and then even if you can't apply them directly because it's not the same system, you can get some understanding about what's going on. It's worth pointing out that, in my experience, training supervised systems is something you can do right now and be pretty guaranteed it's going to work. You can get something interesting. If you have a good data set, then you can get a system that will work within reason. But, however, unfortunately, I have to say this is a lot more difficult. These are kind of iffy about whether or not they'll converge at all, whether they'll take forever. For instance, to train these Atari games takes something like 3 to 4 days on a GTX 970. So if you have a GPU cluster, you're good, but training for an individual game for 3 to 4 days straight, it makes your iteration a little bit slow. So, yes? Yes. So, in general, back to the sort of philosophical discussion of openness of AI and whether or not an individual can contribute, it's certainly true that an individual can contribute now. But one of the disadvantages they have is, as you get these models that depend upon more and more of having a whole cluster of GPUs or a whole cluster of ASICs, which is what Google has, it becomes a little bit more difficult for an individual to contribute. That's not true yet. It just might be true in the future, or rather, it's not obviously true yet. In fact, AlphaGo was run on a cluster of Google ASICs, which might explain why people are having some difficulty reproducing it. Now, on the other side, you have the fact that with supervised learning, what you need is a good data set, and Google has the good data sets too. So, something to keep in mind. The advantage of reinforcement learning, especially with game systems, you can produce all the data you need.
Is there anyone that's been talking about commercially deploying ASICs with Google ASICs? Is there anyone selling them?
Yeah, Google Cloud allows you, Google Cloud runs off of their own ASICs in many cases, with their machine learning cloud. So you can effectively benefit from Google, but having to go through them. So I haven't seen anyone selling the ASICs on their for machine learning. I wouldn't be surprised if it happens, but it's difficult to get the scale necessary. It's possible that Pascal with half precision will make that more accessible. It's not entirely clear how much of an advantage Google's ASICs have. It's quite possible that they're basically just a stripped down GPU, where they throw away float 32 and 64 and only have float 16 or even 8, because typically you don't need that much precision when doing neural networks. So you can get you can fit twice the size models, get more speed by just focusing on float 16, for instance. And fortunately, Pascal, which is the new NVIDIA GPU architecture, probably will have support for double speed float 16. And so that might bring it closer to what Google's ASICs are getting now. Yes?
What different areas do you see deep learning being used heavily in the next 5, 10, or 15 years? Where's it going?
I think it will be. I think it will be used in a lot of different things because, in many cases, even supervised systems can be considered as a reinforcement system beneficially if you had the algorithms to solve for it. For instance, when you have a data set, when you train on part of the data set, that is kind of like taking an action and by deciding to explore that region of the data set. So if you can have a good exploration strategy, then you potentially apply that to exploring your data set to train on, rather than just in a game sense. I do think it's also beneficial in a lot of systems where if you have a general learner, then you can solve little control problems like we were discussing before. Like for instance, balancing your quadcopter is a control problem that has actually been solved pretty well. But you have a new system. Instead of having to try to reapply or remake your control system, you can just slap a learning model on it, and it'll learn how to control your new unwieldy, abomination. So I think that it will be used a fair bit. Probably not as much as supervised learning in the near future, just because it is a lot more difficult and it takes a lot longer typically to train.
How do you think it will be different if you use hardware? For example, the Atari games, what is the use they use?
I'm sorry, I'm having difficulty hearing you.
The Atari games, they use game differently if you use the hardware, like the real computer, then you use
So there would be difference because of the analog inputs and the just differences in the hardware. That's more the physical complications of the continuous space, possible action space. I don't think that it would make any fundamental difference, but I think it would be more difficult, and it would take a lot longer, of course, because physically pressing buttons takes a lot longer than taking actions.
what if we use the software to be able to catch up?
I think it would be able to, yes. I haven't tried it, but my guess is that it would be able to, especially if you trained it first on the software and then put it on the hardware, that it'd be able to learn what was wrong and accommodate. That is a typical tactic, by the way, is train something, a general model on something, on a part of a problem that has some similar problems, and then you want to use one of the similar, want to train for one of the similar problems, and you take your pre-trained model and start training it on the new problem. And since it's already sort of learned most of the important stuff, then it will train much faster, typically. It's like,
Any recommendations for how to set up hyperparameters, because there are a lot of hyperparameters I see which definition takes a few days to run, then if it doesn't work, you have it's very hard to find out which one of these hyperparameters is off.
yes, so there are hyperparameter optimizers, but obviously if it takes a really long time to run, then those may or may not be a good idea. For instance, if you take a Bayesian hyperparameter optimizer like Spearmint and run it, then it'll probably come to something pretty good. But it'll take a long time, so you might want to initialize it with your own estimates. I'd recommend focusing on figuring out what the minimum problem is you can do, i.e., if you're looking at something, this is unfortunately where you have to do some manual work, but for instance, if you're looking at a game, can you cut it down and make it try a small section of the game so that you can just see whether what you're doing works at all. You want to iterate as fast as possible, so whether your model is working at all. In general, the larger the model, the better it will work. As in, if you are just doing your actual model, your deep neural network or non-deep neural network, which is usually the model that we're talking about. The larger, as in the more neurons and the more hidden layers, the better. Depending on the type of problem, you might want to make it more of a deep neural network or more of a wide neural network, i.e. more layers versus more neurons. Generally speaking, if you make it as large as will fit on your GPU, that will perform the best. However, it'll also take longer to train. So that's a trade-off. And then you can have to consider, there's honestly no like hard and fast rules. There's sort of rules of thumb. So some problem sets are more amenable to a deep neural network, which typically are things with more complicated rules, more complicated consequent dependencies. So if you have something that's basically might have a very large search space, but is fundamentally a simple problem, like, you know, look at this and identify and go to the one spot that has the fruit, for instance, then that's a relatively simple problem. But if you have something where, with a lot of complicated dependencies, then you might need a deeper model to accommodate it. For instance, and these can get very deep, for instance, with images, which tend to be the deepest models that I know of. Image analysis tend to use the deepest models. With residual learning, which is basically a form of ReLU, they've managed to train extremely deep networks, like 150, 260 layers, and they tend to perform better. So we haven't really reached the limit of how good, for certain problems, it's better to make it deeper. So in general, I would try a couple of different architectures. As far as things like which optimizer to use, how fast to decay, how to explore how fast to decay your epsilon, what type of activation. ReLU is very common. I think that's probably a good default. Using something like RMS prop for these games is common. And even then it can be a little bit complicated because, for instance, DeepMind has their own implementation of RMS prop, which is probably better, maybe. It's a little bit tough to tell. So I would try, in these libraries, typically it's really easy to define which optimizer you use, which layers you use. So if you can figure out a way to cut down problem space, else what I would do is look up this similar problem in papers that you can find and use what they used first. Any other questions? Yes?
How much is machine learning being used in human computer precision language?
So, for instance, with the TD Gammon and AlphaGo, I mentioned that they can learn problems, they can learn solutions to the games that we never thought of. It's certainly being used for things like, that. You can also look at some of the more complicated problems, like when you look at recommendations, for instance. You can look at a lot of different information that a human just couldn't really process. And it will determine what's actually important for recommending, say, a new movie to someone. And so you can learn some interesting things about what actually is important to the problem when you just have a bunch of data and you're like, I don't know. I saw an interesting thing on, someone was making a categorizer for archive, which is the physics paper pre-publishing Anyway, they made a categorizer, and they found that, to try to split into different categories on the site, and they found that the ones that were uncategorizable, that it didn't have good confidence in its categorization, tended to be the crank papers, which makes sense when you think about it, because it was basically reading the papers, and the type of language that was being used in the crank papers was just not matching the other sets, so it tended to be uncategorizable, which is interesting, and you can potentially, and it's been used, for instance, in the natural language processing to identify parts of speech and stuff that a human can't necessarily see. I think I need to go. Any last quick? All right. Thank you very much.